So if this circuit, we have already studied LCR series circuit in the last
Yes,
class.
sir. Yes.
So those concepts I will use here. So
Yes, sir.
I have told you that in that case, if you will draw the phasor diagram, for LCR series circuit, so this type of phasor diagrams you will get. These types of phasor diagram you will get, okay? And
Yes, sir.
what is XL? XL is
Less
basically the
inductance.
yeah, inductive reactance, and
Yeah,
XC is
inductive
the
reaction.
and
Capacitive
X,
reaction.
yeah, R is the resistance. So in this case, current and the resistance are in the same direction, but the inductive reactance is leading the current by 90 degree, and
Yes, sir.
capacitive reactance is lagging the current by 90 degree. In terms of the voltages, these are the basically the peak voltages. Okay, so this is the
Yes, sir.
peak voltage in case of inductor, peak voltage across the resistance, peak voltage across the capacitor, already discussed. So this will be the phasor diagram, and
Yes, sir.
in this case, this is the peak voltage across the resistance is in the direction of the current in the circuit. Okay,
Yes, sir.
and peak voltage across the inductor is leading the current by 90 degree, and here in case of the capacitor, voltage across the capacitor, peak voltage across the capacitor lagging the current by 90
90
degree.
degree.
Okay, so basically this angle and this angle is 90 degree. Now this case I have discussed in the last class. This case also I have
Yes.
discussed in the last class, but I have told you the third case I will discuss later. So now today we will discuss the third case, and third case is basically the condition of the resonance. Condition of the resonance when XL becomes XC in the LCR circuit. When XL becomes equal to XC, XL means inductive reactance becomes equal to the capacitive reactance. So
Yes,
basically,
sir.
this is the condition of the resonance. This is the condition of the resonance. So remember this point only. Okay,
Yes,
remember
sir.
this point. Okay, so equation of the voltage I have written V is equal to V naught sin omega t. Equation of the current is this, I is equal to I naught sin omega t plus phi. Phi is basically the phase difference between the current and the voltage. Okay, phi is
Yes,
basically the
sir.
phase difference between the current and the voltage. Okay, so phi is the phase difference between voltage. What voltage? Net voltage of the circuit. Okay, net voltage of the circuit, phase difference. So at resonance, this XL becomes equal to XC. So at resonance, what will be the frequency? Easily now we can calculate the things very easily. Okay, frequency. We will calculate impedance in case of the resonance. After that, we will calculate the cost power factor, power at the resonance, and we will see some of the graph. Okay. Okay. Uh, can you give me just 2 minutes? I am just coming.
Yes, sir. Yes, of course.
So remember, this is the condition we will discuss. XL is equal to XC.
Yes, sir.
XL is equal now. At resonance, first we will find frequency. Now see how we will find frequency. Very easy to calculate. We know that at resonance XL is equal to XC na. So what is XL? XL is equal to omega into L.
Yes, sir.
XC is equal to 1 upon omega into C.
Yes.
Now we can multiply this with this. It will become omega square into LC is equal to 1. So I can write it as omega square is equal to 1 by LC. Okay. So from here
Yes,
you
sir.
will get omega is equal to 1 divided by under root of LC. So
Yes, sir.
this is your angular frequency at resonance, and I will represent this angular frequency with omega naught. Omega naught is the angular frequency at the resonance, and this is known as the resonant frequency, resonant angular frequency. This
Yes,
is
sir.
known as the resonant angular frequency. This is known as the resonant angular frequency. This green color is okay na? Visible na?
Yes, sir. Yeah. Yes, sir.
Okay. So first formula, this formula you have to remember. They can ask you in the examination what is the resonant angular frequency. Okay. After that, there is a relation between the omega and frequency, angular frequency and the frequency. There is a relation
Yes,
that is
sir.
given by omega is equal to 2 pi into f.
Yes, sir.
This is the relation. Na? So we can write omega naught is equal to 2 pi into f naught.
Yes, sir.
What is a f naught? F naught is the frequency at resonance. So f naught, from here we can find omega divided by 2 pi. So what is the value of the omega? Omega is 1 upon under root LC. So from here we will get frequency f naught is equal to 1 upon 2 pi under root of this is omega under root of LC into 1 upon under root of LC. So this we will get 1 upon 2 pi, or you can write in this way also. It is better to write in this way. It will look good. It will be 1 upon 2 pi LC. So what is this? This is the frequency at resonant, or this is also known as the resonant frequency. So if someone is asking what is the resonant frequency, formula is very easy. You can say 1 upon 2 pi under root of L into C. What is L? Inductance. What is C? Capacitance. Now,
Yes,
if
sir.
someone is asking what is angular frequency, define the resonant frequency, then you will say this is the frequency. This is the frequency in an LCR series circuit of the voltage or the current at which the capacitive reactance becomes equal to the inductive reactance. Okay, so capacitive reactance is becoming equal to the inductive reactance at a particular frequency, that is known as the resonant frequency.
Resonant frequency. Yes, sir.
Yeah. So this is the another formula you have to remember. Now, what was the formula of the impedance we have calculated? Z is equal to under root of R square plus
Yes, sir.
XL minus XC square. But at resonance, we know that XL is equal to XC. At resonance, we know that XL is equal to XC when this XL becomes equal to XC. When this XL becomes equal to XC, so this term will become 0.
Yes, sir.
So you will have Z is equal to under root of R square. So which basically impedance of the circuit Z is equal to R. Impedance of the circuit Z is equal to R. You have R. So at resonance, there is no capacitive reactance, there is no inductive reactance, only resistance is present in the circuit. So you can say the resonant circuit will behave as a resistive circuit. Okay.
Yes, sir.
Circuit behaves as purely resistive circuit. Purely resistive circuit. Now you can see at resonance this Z is equal to R only. This terms become zero. This terms
Yes, sir.
become zero means at the resonance condition, this Z becomes minimum. Impedance of the circuit becomes minimum.
Minimum, yes.
Yeah. So we can write at resonance Z becomes minimum. Why minimum? Because you can see from the formula this term is becoming zero.
Yes, sir.
That is why Z becomes minimum. And if Z becomes minimum, then what can you say about the current? Peak current in the series LCR circuit is given by current is equal to the peak voltage divided by the impedance, and this impedance, when Z will become minimum, so if this value will become minimum, then current in the circuit will become maximum, then peak current in the circuit will become maximum. So current in the resonance condition is given by I naught max is equal to V naught divided by R only. Okay. Why R? Because Z is equal to R in case of the resonance. So Z is equal to R. That is why I have written this. Okay. So this is the next thing. Now, if I want to calculate the phase difference phi between the current and the voltage, phi I want to calculate at resonance. So see how will I calculate. So we know that cos phi is equal to R by Z in the last class.
Yes, sir.
If you remember, you know that cos phi is equal to R by Z, but in case of the resonance, Z can be written as equal to R.
Yes, sir.
So this is R. Instead of this Z, you have put the value of R, and R equal to R and R will be cancelled out. You will get cos phi is equal to 1.
Yes,
So
sir.
cos phi is 1 at phi is equal to 90 degree. Phi is equal to 0 degree. So what will be the phase difference? Phase difference between the current and the
Zero.
voltage in case of 0 degree. 0 degree. So basically this phi is the phase difference at resonance. Phase difference. Now power factor is cos phi. So power factor, if you will calculate cos phi, that is equal to 1. Okay? Because cos 0 is equal to 1. So power factor
Yes,
is
sir.
1. Now power at the resonance. Power of the circuit, we calculate average power. No? So average power is given by Vrms, Irms into cos phi. Okay. So now what is the value of the cos phi at resonance? That is equal to 1. So average power will become is equal to Vrms into Irms.
Yes, sir.
Vrms into Irms only. And basically this average power will be the maximum power, because cos phi will be, when cos phi is equal to 1 means 1 is the maximum value of the cos.
Maximum value of course.
Maximum value of cos. So this is the power at the resonance. Okay. So if you can convert this value in terms of the peak value. Okay. So we know that Vrms is equal to V naught by root 2, and we know that Irms is equal to peak value of the current divided by root 2. So
Yes,
now
sir.
put the value here. So average power at the resonance, that is the maximum power, is equal to V naught by root 2 multiplied by I naught by root 2. So it will become average power at the resonance, that is maximum power, is equal to V naught into I naught. What will be the value in the denominator? When you will multiply root 2 and root 2, it will become
2.
2. Very good. 2. So basically, this is the maximum power at the resonance, or you can say power at the resonance in terms of the maximum value of the voltage. Okay, so you can write either in terms of the RMS value, or either you can write in terms of the peak value. V naught and I naught, na, you know what is V naught and I naught.
Yes, sir.
I have
Yes.
told you peak V naught and I naught represent the peak value.
Peak
So,
value.
so these are the things. And what is the phi? If I will say phi here is 0 degree. Phi is equal to 0. At resonance, phi is equal to 0. So there is no phase difference at the end the current in case of the resonance. So if
Yes,
there
sir.
will be the condition of the resonance, I have told you this XL becomes equal to XC. So you can just imagine this two vectors are acting in opposite direction. So this XL will be cancelled out by this XC. So this will be only the phasor diagram. Okay. So this will be only the phasor diagram. Now this voltage and this voltage in magnitude will be equal. So this will be cancelled out by this. So this diagram will be. And what will be the voltage at the resonance? What will be the voltage at the resonance if someone is asking value of the voltage at the resonance? What is the value of V naught? V naught is equal to I naught into Z. And V naught is equal to I naught. What is Z at resonance? Z at resonance is equal to I naught into R. And what is I naught into R? Peak voltage across the resistance. So that is why I have written this. So basically this is equal to V naught.
Yes, sir.
You have to understand the whole phenomena what is happening here. All of the things is happening when the frequency is becoming such that the inductive reactance of the circuit becoming equal to the capacitive reactance. So all these conditions, this is the special condition basically. So why this is a special condition? Because in this condition the resistance of the circuit becomes minimum and there is a maximum current in this case. There will be the maximum current and there will be the maximum power. Okay, Harsh, so now you can note down it.
Yes, sir. Second student.
Hold on. So remember, I have already told you this thing in detail. We have one
Yes,
whole
sir.
lecture on this.
Yes, sir.
So
Second scroll down.
Yeah. Harsh, are you available tomorrow? Or you are going
Yes, sir.
somewhere?
Yeah, I'm available on tomorrow.
You are
No, no,
going
I'm
somewhere?
available tomorrow. No,
You are
sir. I
available.
just yeah, I'm available.
So
Sir, I
okay,
went. Yeah.
okay. So I will let you know the timing of tomorrow. Okay. So
Yes, sir. You can take it because
yeah,
Saturday
we
I will go, so you can keep the class tomorrow.
yeah. Okay. So timing I can tell you. Okay.
Yeah.
I will tell you the timings means according to the
Sir,
my
if you
timings
can
and
keep in the morning, you can keep in the morning also. If you
morning
want to.
IST.
Morning
IST.
IST, yes.
Okay. So do you have my phone number? So you can just write.
Uh,
You can just write there hi, and I will get to know. Okay. Then we
yes, sir.
will
I have
discuss
a phone
there.
number. I have. No, sir. Actually, you can just keep in the say at the at evening also, sir. Because morning I have practice. Sir. That's why.
Okay, okay. Morning. I am not saying in morning. I will take the class. Okay. Depending, I'm just saying, na, according to the mic timings, according to the timing, we will just negotiate that. We will discuss that.
Sir, can we keep it same time if you have the time? Same time if you're free.
If
If you're free.
if I will free, actually tomorrow is my not the working day. So okay, we will see whether I will be free or not. I will let you know. Okay.
Yes, yes. You can surely.
Yeah.
Sir, I'll message you. You can tell me the timing.
Huh.
Okay, second student.
Yeah.
Second, scroll up for a minute. Just a little bit up.
Up. Okay.
Yeah, just a minute. Sir, a little bit more, sir.
Okay. Okay. No problem.
Yeah, that's it. Thank you. Just a minute. I forgot to write the resonant frequency.
No problem.
Okay, sir, you can scroll down, sir. Last topic.
Okay. No problem.
Take a scroll down.
Okay.
Done, sir.
Done. Okay. Write down this power at resonance. Done. Harsh, completed.
Yes, sir. Yeah, done, done, done.
Okay, so this is the all the data means frequency we have calculated. We have calculated the what will be the impedance, and you can say from the impedance you can say what about the current. Current is related
Yes,
with
sir.
the impedance. So here current in case of the resonance will be maximum. You have to
Yes,
remember this point first. And after that, what is the power factor and what is the power at the resonance? Now there are some graphs that may be asked in the examination. Very simple graphs. With the help of the formula, I will explain how
yes,
to draw the graphs. Okay. So basically, first graph is we have already drawn, but again I am just drawing these graphs. Okay. So basically, first graph, we know that XL is equal to omega into L, and omega can be written as 2 pi into frequency. It will be L. This is L. So XL you can say is directly proportional to frequency. So the
yes,
graph
sir.
of XL versus frequency will be like this, a straight line passing from origin like this.
Yes,
So
sir.
this will be the graph of XL. Now for XC, you can write 1 upon omega C, and omega you can write 2 pi into F, and this is C. So XC, basically this is C. So XC is inversely proportional to frequency. So for the graph of XC, you will get this type of graph. Oh, it is very difficult to draw this graph by this pen. This type of rectangular hyperbola type graph you will get. Okay, and
Yes, sir.
and resistance is independent with the frequency.
Yes, sir.
Resistance is independent with the frequency. The graph of the resistance will be like this. Graph of the resistance will can be like this. This is for the resistance, and this is for XC. And here is very important point we got. This point of intersection. This is the point of intersection where where there is a frequency at which XC is equal to XL. See how beautiful this graph is. Means here both the XL and XC at this point becomes equal, and this is the condition of resonance. This is the condition of resonance, and here you are getting the resonant frequency. Is it or not?
Yes, sir.
So XL is equal to X, and what is F naught here? resonant frequency na,
Resonant
f naught,
frequency.
yeah, f naught here is the resonant frequency. Now there is one graph between the impedance and the frequency. And how you will say, sir, how you have drawn this graph like this? Okay, I'm showing how this graph is like this. We know that Z is given by R square plus XL
XL minus XC
minus
whole square.
XC square. Okay. So resistance is a resistance, but XL can be written as 1 upon 2 pi into F into L minus 1 upon, it can be written as 2 pi into F into C. And this is the square of this. Okay. Now see the frequency. This is Z. This is Z. This Z, and see the Z and frequency, because this graph is in between Z and the frequency. Now when you will start from this point, okay, start from this point, and when you will suppose increase the frequency, na, when you will increase the frequency
Yes, sir.
uh, beyond this uh, resonant frequency, f naught is the resonant frequency. When you will just increase the frequency beyond this uh, f naught, so what you will get basically, in not in this way I will explain you, with some different way I am explaining. If you are increasing frequency, if you are increasing frequency, suppose you have taken any value of the frequency, okay, if you will
Yes, sir.
take if you will take a small value of the frequency here, so this whole term will become small. Okay, if you are taking a small value of the frequency, this whole term will become small,
Yes,
and
sir.
this, okay, here this whole term will become small. So basically this impedance here will become small. Okay.
Yes, sir.
Uh, okay, for example, I want to say that if I am taking f small, if I am taking f small, okay, then see this z, okay, what is happening here? If you are taking this small, so this whole value will be small and this whole value will be small. Okay, so basically uh, z will become large. Okay,
Yes, sir.
why z will become large? Because this whole value will be somewhat get increase. Okay, this whole value will be somewhat get increase. Okay, so
Increase.
this z will become large. Okay, if you are taking the frequency large, if you are taking the frequency large, then also you will get the z large.
Yes, sir.
Why you will get the z large? Suppose I have written 1 upon 5 and plus 1 upon 5, and I have written 1 upon 26 plus 1 upon 26. So basically what I getting here, I am getting 2 by 5, and here I am getting 2 by 26. So basically in both the cases, in the numerator there is 2. If I am taking a large number or a smaller number, okay, there will be no effect on the numerator. So basically,
Yes.
so you can say if the frequency will large, then also the impedance will in large. Okay, but there will be a frequency, at which this value becomes equal to this value,
Yes,
and
sir.
here the impedance of the circuit becomes minimum, that is z equal to r. Okay, that is become equal to r. So basically this graph will be like this. First, when you will increase the frequency, when you will increase the frequency uh, below the f naught, then impedance will decrease. Okay, when you will increase the frequency after the f naught value, then impedance of the circuit will increase. Okay, here the impedance is decreasing, here the impedance is increasing.
Increasing.
Okay, yeah. Okay, if I will draw a graph between the current and the frequency, so you can see here the current and impedance are inversely proportional. So this graph will be
Yes.
just reverse of that. This graph will be just reverse of that.
Reverse.
So basically this
It
is
will
the
increase
type.
before F0 and
Yeah,
decrease
you
after
can
F0.
see here, if you are increasing the, if you are increasing the frequency before f naught, so impedance is decreasing. But here if you are increasing the frequency beyond f naught, the current is increasing. So you can say this
Yes,
is
sir.
just the reverse graph. Okay,
Yes, sir.
so this is the maximum current, this is the maximum current at the resonance. Okay, if you will draw the graph between the average power and the current, same graph you will get, because power is equal to I RMS square into R. Okay, so this will be the I RMS into Z. Okay, so you will get the same graph like this. Basically you have to learn how to draw this graph. Okay, in the
Yes,
examination
sir.
they can ask you draw the graph between the power. You should have the little idea how to draw the graph.
Yes, sir.
So these are the graphs basically, average power, and this graph I will use later. Okay, so first just complete these graph, then I will just discuss the further details.
Yes, sir.
Okay, there is one slight mistakes we have done. Actually, this value will be, XL is 2 pi FL. Okay, so now you can write down.
You can scroll down.
Hmm. Hus, do you know what is angular velocity?
Yes, sir, omega.
Angular velocity.
So yes, hold on. So yes, hold on.
So you can see from this graph at f naught, this f naught is the resonant frequency. At this f naught, the power is maximum in
Yes,
the
sir.
circuit. Okay.
Done, sir.
Done. Okay. Okay. Now, this we will discuss sharpness of the resonance and the bandwidth. Okay. So this topic we will discuss now. So this is the graph between the current and the angular frequency. This type of graph we will get here will be the angular frequency, and at this point now I am just drawing the graph in terms of the omega, so it will be omega naught. So you can see earlier also when you have drawn the graph between the current and the frequency only, so you are getting this type of graph, and you know that the frequency and omegas are related to each other, okay, directly proportional to each other. Then you can draw the graph between the omega and current, okay, omega, and this is the current in the circuit. So at this point you will get the maximum current. So this is omega, where you will get the maximum current, and there will be the current, there will be the current. Okay, I will draw this. Remember what I want to say, focus. There will be a current for which there will be a angular frequency. Suppose this is omega 1 and this is the angular frequency. Suppose this is omega 2, and this current is the root 1 upon root 2 times of maximum current. This current is I max divided by root 2. This is the maximum current. Okay, it is better to write it as I naught max because we are talking about the peak value of the current. Okay, it will be I naught into maximum current. So here the current is basically I naught of max, and here it will be I naught max divided by root 2. So here the current is I naught maximum divided by root 2. Now basically at this current you will get the half power of the maximum power. What is the maximum
Yes.
power I have told you?
I not. Sorry.
No,
maximum power.
VRMS,
Yeah. Sorry.
or you can just write in terms of the V naught I naught by 2.
Yeah.
So I have told you V naught into I naught divided by 2. This is the maximum power at resonance. Okay. Now suppose what you have to do here, you want to find the maximum power at this current. Now you will see this power will become half. This
Yes,
at
sir.
I naught by root 2, this power will become half. See how this will be happen. This is v naught now. So v naught can be written as I naught by z. Okay.
Yes, sir.
So this is I naught, and what is z at resonance? Z is equal to r. So basically v naught can be written as I naught divided by r. So P max is equal to V naught is basically I naught divided by R into
Yes,
I
sir.
naught by 2. So maximum power you will get I naught square by uh, RZ, 2R. I naught square by 2R you will get. Now when you will put the value of I naught is equal to I naught by root 2. So see what will be the value of the power, maximum power. So put the value, it will be 1 upon 2R, and it will be I naught by root 2 square. So now see, it will become maximum power, it will become 1 by 2R, and it will become I naught square by 2. Now you can see this is I naught square by 2R is maximum power.
Yes, sir.
Okay, basically this is suppose the maximum power 1 or dash. This is maximum, another maximum power. So basically, what is the maximum power you are getting? Half of the maximum power you are getting. At what current? This is the power at current I naught max by, for the maximum current divide by the under root 2. Basically, this is the
Yes,
power.
sir.
So basically, I want to tell you na, this omega 1 frequency, omega 1 and omega 2 are known as the half power frequency. So I have just given this the basic idea, okay? Half power
Yes, sir.
frequencies. Half power frequency. And how the half power? Because at this value of the current, the value of the power will become half. So I think now you have understood. So no need to write it down. Okay. So omega and omega 2 are the half power frequency. How I have told you half power frequency? Because this is half power current. So corresponding to the current, there will be the half power frequency. Now there is a term bandwidth. I have already written this thing here also. Okay, so
Yes, sir.
bandwidth is basically this omega 2, I mean the difference of half power frequency, and this is known as the R by L. Bandwidth is delta omega is known as the bandwidth, and this is R by L. Basically, for the practical purposes, we want the small bandwidth. Okay, for a small bandwidth, the resistance should be small at the resonance,
Yes, sir.
because bandwidth is depending upon the resistance and the inductance. So resistance should be small at the resonance and inductance should be large. Okay, so resistance should be small. Okay, so now from here you can see how I have written this result. Basically, delta omega is equal to R by L. What is delta omega? Delta omega is basically this distance. You can see here. Just a minute. This distance is the delta omega. This distance is delta.
Delta omega.
Yeah. Now, uh, this is omega naught. Now, this is the omega naught, and this is the origin value. This is the reference point origin. So now, if I want to write omega 1, or suppose if I want to write omega 2, so omega 2 is the this distance. So this distance can be written as omega naught, and delta omega is R by L. So delta omega is this distance, half of the delta omega is this distance and this distance. So basically this distance is basically R by 2L, and this is also r by 2l. How this is r by 2l? Because this is delta omega, and delta omega is r by l, half of r by l, half of r by
R by
2l, r by
yeah,
2l.
2L.
Okay, so if I want to write omega 1, so I can write omega 1 as omega naught minus this distance. So I can write omega naught minus r by 2l, and for omega 2 I can write omega naught plus this distance, that is r by 2l. So this result I have written here. Okay, this result I have written here. Okay, so there is another term, quality factor. So quality factor is known as the resonant angular frequency divided by the delta omega.
Delta omega.
Now we know what is delta omega, and we can find it. Omega naught. What is the value of the omega naught? I have tried omega naught is equal to 1 upon under root L by C, and delta omega is equal to R by L. So we can solve it. It will become 1 upon under root LC multiplied by L
Yes, sir.
by R. Okay, so here I can write this will be under root L. So here you will get, basically this can be written as at under root L into under root C into R. Okay, and here is L. So L can be written as under root L into under root L.
Yes, sir.
1 under root L, 1 under root L will be cancelled out. So basically Q factor, finally you will get 1 upon R under root of L by C. So this will be Q factor or quality factor. So this is the formula for the quality factor. Okay, for increasing the quality factor, resistance should be small,
Yes, sir.
and inductance should be large, and capacitance should be small. Okay. So you can now note down this.
So you can scroll down. scroll down.
Hmm.
Done, sir.
Okay. Okay. So next topic is the transformer. Okay. So basically, two types of transformers are there. And first, you should know what is transformer. Basically, transformer is a device that transforms the voltage. Transforming the voltage means converts the low voltage to high voltage and high voltage to low voltage. Okay. So a transformer that transforms the low voltage to the high voltage is known as the
Step up transformer.
step up transformer. A voltage
From high to low is
high to
step
low is
down.
step down transformer. So this
Yes.
transformer is based on the principle of mutual induction. We have discussed mutual induction in electromagnetic induction. There I have
Yes, sir.
uh, shown you that two coils are there. If you will change current in one coil, there will be the induced current in
Yeah, change in the other coil. Yes.
another coil. So before the understanding the working of the transformer, you should know what is solenoid and what is a magnetic field in the solenoid and what is the magnetic flux. Suppose
Yes,
this
sir.
is a solenoid, and if you are saying that this is a solenoid, so the magnetic field of the solenoid, the magnetic field, oh sorry, the magnetic field of the
So just a
solenoid.
minute, sir. Just a minute. There is a disturbance. In the just a minute. So can you hear me?
Yeah.
Yes,
Can
you
I
can
start now?
continue. Yeah,
Okay.
you can
So
continue.
solenoid is this, and in this solenoid there is a current I, and the magnetic field inside the solenoid is along the axial direction. Okay,
Yes, sir.
along the axis of the solenoid in the axial direction, and magnetic field in the solenoid is given by B is equal to mu naught into I. Okay,
Yes, sir.
and the magnetic flux is VA cos theta. This formula you have to remember. Okay, VA cos theta. And what is theta? Theta is the angle between the area vector and the magnetic field vector.
Yes, sir.
I have told you this thing so much, so many times. Okay. So now this is the transformer. Basically, what is happening here in this transformer? First, we have taken a soft iron core. I will show you how this I have drawn this. So basically, this is like this and like this. This is a soft iron core. This thing is a soft iron core, and after that, what we have done, what I have done, I have just winded this like this. Winding of wire is done on this. Okay, winding of wire is done like this. So basically, this is the primary winding. This is the secondary winding.
Yes, sir.
So this is the basic diagram of the transformer. Okay, so here, what we have done, we have taken this white color thing is the soft iron core, and here is the primary winding like this, and this
Yes, sir.
primary winding is have some input voltage. Okay, input voltage means some supplied voltage, alternating voltage is there, and this is known as the primary winding. So primary winding. Okay, so this is known as the secondary winding. So this is primary winding, this is secondary winding, and number of turns in the primary winding, this NP, and this is the secondary winding, and here we are getting some output voltage by the
Yes,
action
sir.
of mutual induction. Okay, so NS is representing the number of turns in the secondary winding. Okay, so now see whole phenomena. What is happening here? Basically, this input is the alternating voltage. So due to this alternating voltage, there will be the alternating current in this winding.
Yes, sir.
And due to the current, I have told you there will be the magnetic field inside the solenoid. So basically, this is a solenoid. Winding is like a solenoid.
Yes, sir.
So these are these blue color lines are representing the magnetic field inside the primary winding. Why there is a magnetic field inside the primary winding? Due to the current in the winding.
Winding.
Okay,
Yes,
due to
yes.
the current in the winding. Now, what will happen? This is a soft iron core. So these are the magnetic field line in the primary winding. So due to this soft iron core, these magnetic field line will go to the uh, or go across the secondary winding. Why? Because this soft iron core has a property to confine the magnetic field line within itself. Okay,
Yes,
this is
sir.
the property of the soft iron core. So magnetic field line will be like this. So it will the soft iron core will bend the magnetic field line like this, and finally the magnetic field line will pass through the secondary winding. Okay, and
Yes, sir.
finally the magnetic field line will be like this. Okay, so basically the blue color lines are representing the magnetic field line. And why there is magnetic field line? Because here is the current in this primary winding. There is a current in the primary winding, and due to the current
Yes, sir.
there are the magnetic field, and magnetic field along the axial direction. So this
Yes, sir.
in axial direction there will be the magnetic field line, and these magnetic field lines will be voltage like this due to this soft iron core. Now there is one point here. Here the current is changing because current is alternating current. If the current is changing, then you can say the magnetic field here will change.
Yes, sir.
From this formula, you can say the magnetic field is changing. So now you can say here also the magnetic field is changing, or magnetic field line changing, strength of the magnetic field line changing here also, because same magnetic field line here and same magnetic field lines are here. So what happens when the magnetic field will change? Magnetic flux will change from this formula, BA cos theta. Hello, Harsh.
Yes, sir. Yes, sir. Yes.
If this magnetic field will change, means magnetic flux will change. So here you can say the magnetic field is changing. The magnetic field is changing. Due to that, the magnetic flux linked with the secondary winding is changing.
Yes, sir.
What happens when magnetic flux changes? There will be an induced EMF,
It's induced
and
EMF. Yes, sir.
that induced
And that
EMF
EMF creates a flux.
yeah, induced EMF will be the output voltage. Induced
Yes,
EMF will
sir.
be the that induced EMF when you will multiply with this ns with respect
Yes.
to the coil, then you will get the voltage you will get. So input voltage is this, output voltage is this. Okay, and accordingly there is a transformation of the voltage due to the mutual
Yes, sir.
induction. Okay, what is happening here? Basically, you are changing the current is changing here. Current is changing here, but here is the induced current, and due to that induced current, there will be the induced EMF here. Okay, or you can say you are changing the current here. So due to that current, there will be the change in the. Acha, can you tell me, is there any physical connection between this coil and this coil? There is no physical connection, na?
No, sir. No, sir.
Physically, they are not connected. There will be the
No, sir. They're not connected.
process of mutual induction. Why? Because you are changing the current here. Current is changing here. That is why the magnetic field is changing here. Okay.
Yes, sir.
Same magnetic field lines are here also. Then you can say here also the magnetic field is changing. So due to
Yes,
the
sir.
change in the magnetic field, there will be a change in the magnetic flux. Due to the change in the magnetic flux, there will be the induced EMF here. Okay, according to the Faraday law. So this thing I have written here. Okay, so changing magnetic field is changing due to the change in the current. Okay.
Current.
Okay. So now after that, now you can see, take one coil. There is a difference between the winding and the coil. This one thing is a coil. This is a coil, and this
Yes,
hole
sir.
is a winding. This hole is a
Yes,
winding.
sir.
So you can take, suppose this coil you have taken, and here suppose you have taken this coil. So for this coil and for this coil, you can say number of magnetic field line crossing are same.
Yes, sir.
Three magnetic field lines are crossing here, and three magnetic field lines are crossing here. So you can say, what is the magnetic flux? Magnetic flux is the number of magnetic field line crossing per unit area. So
Yes, sir.
here, so across this coil and across this coil, the magnetic flux is same. So you can say that
Yes.
across each coil of the primary winding and across each coil of the secondary winding, the magnetic flux is same. Okay, so this thing I have written here. Magnetic flux linked with each turn of the primary coil is equal to the magnetic flux linked with each turn of the secondary coil,
Secondary coil.
that is equal to phi. Phi
5.
I have written.
Flux.
Phi is the flux. Okay. So first note down, then we will discuss.
Second, hold on. Second scroll down.
Yeah. Okay, so write down till here, then I will explain what next.
Okay.
Now the story till here is clear.
Yes, sir.
What is happening means uh, you have to understand now how the mutual induction is taking place here. You have to understand why I am saying why I have written this statement. You should have a picture in your mind. Okay, why I
Yes,
have
sir.
written this. I have written this because the flux with each turn or each coil of the primary winding is equal to the secondary winding. Not,
Yes, sir.
I am not saying that the magnetic flux linked with the secondary winding is equal to the primary winding. I am not saying that. That is totally different thing. That is totally different thing. I am
Different things.
saying with each coil, the magnetic flux will be same.
Yes, sir. Done, sir.
Okay. Okay, because number of turns are changing. So magnetic flux will be obviously changing now. Completed. After that, uh, we will move further. Uh, okay. So after that, suppose I want to calculate the total magnetic flux in primary winding. Okay.
Yes, sir.
Total magnetic flux in primary. I can write primary now for primary winding.
Yes, sir.
Okay, I can write it. Okay, no problem. Winding. And this is equal to phi suffix p. And okay, this is very easy to calculate. For coil, for one coil, the flux is phi. For one coil, the flux is phi. And for how many coils are there? NP coils are there.
Yes, sir.
So for total flux, this will be the total flux in the primary winding. Number of coil multiplied by the flux for each coil. Not good. Got it or not?
Yes, sir. Yes, sir.
Basically, see, in one coil, this is one coil, and for this one coil, the flux is phi.
Five.
And
Yes.
how many such coils are there? NP such coils are there.
NP.
So total flux will be NP into phi.
Yes, sir.
So it will be NP into phi. So for the secondary winding, you can write NS into phi. This is the phi. What is the meaning of phi as? Total flux in secondary winding. Okay, total flux in secondary
Yes.
winding.
Secondary winding.
Now, if I want to calculate, okay, so tell me here also there will be the change in the flux.
Yes, sir.
So what happens when there is a change in the flux? EMF will be induced. So first we will
Yes.
calculate EMF induced, EMF induced in primary. That will be represented by EMF in primary, and if this is given by Faraday, d phi p by dt, and it will be minus d by dt of What is phi p? Np into phi.
NP,
So
yes,
it will become minus of Np into
NP by
d phi by
d phi by dt.
dt. And secondary you can write d phi s
d
by
phi by
dt.
ds by dt.
Yeah, it will become d by dt of phi s is ns into phi.
ns phi is equal
And
to ns d phi by dt.
dt. Okay. So induced EMF in primary winding is equal to this.
Yes, sir.
Induced EMF in secondary winding is equal to this.
Yes,
Now
sir.
divide ES by EP. When you will divide it, you will get
So d phi by
NP
dt
by,
will cancel out, right?
yeah, very good, very good. NP by
And
NS
NP
you will
Maya NS.
by NS is you will get, and basically this is the expression. First expression we get. What is ES? You can say ES is just the voltage in the secondary winding. EP
Yes,
is the
sir.
voltage in the primary winding.
Primary binding.
Yeah. But ES is the input voltage. ES is the output voltage.
Output voltage and EP is the input voltage.
Output voltage. Okay, this is and EP is the
Input
input
voltage.
voltage. One more name you can give it: voltage in secondary winding and voltage in primary winding.
Primary binding.
You can say voltage in secondary, and you can say this voltage in
Primary.
primary. This then you can say. Now, if I will say that, this is the relation, okay, and this relation
Yes.
you have to remember in case of the transformer. If I will say that there is a transformer called the step-up transformer.
Yes.
So in step-up transformer, which one will be greater? ES will be greater or EP will be greater?
In step up,
Step up means,
ES.
yeah, ES will be greater than EP.
Yes, sir.
So if ES will be greater than EP, then you can write this as ES by EP must be
Yes.
greater than 1, and ES by EP is equal to NS by NP greater than 1. So you can write number of turns in the secondary winding is greater than number of turns in the primary winding. So in step-up transformer, remember this. Number of turns when in secondary winding will be greater than the primary, that transformer will be step-up transformer. Step down.
Step down, it will be NP greater than NS.
Yeah, right. EP greater than ES, EP greater than ES, and so you can conclude that NP must be greater than NS. Means
Yes,
when
sir.
the number of turns in the primary winding is more, when the number of turns in the primary winding is more, means that transformer is step down transformer.
Yes, sir.
Can be a transformer 100% efficient transformer can be there?
100% efficient?
Yeah. No.
No.
Nothing in this world can be 100%. Nothing. Nothing
Yes,
means
sir.
nothing.
Yes.
Okay. No machine, anything you cannot be. It can be 99.999%, but cannot be 100%.
Yes, sir.
Okay. So the Dettol kills the 99.999% of the germ. Dettol can also not clean up or kill the 100% of the microorganism.
Yes, sir.
So this is a rule of the nature. This is valid everywhere. In case of the transformer, in case of the Van de Graaff generator, in case of the AC generator, everywhere. So basically, we are considering the ideal transformer. So what
Yes,
is the
sir.
meaning of the ideal transformer? Ideal transformer, a transformer which does not exist in the real life, and that is 100% efficient. Then you will say, why we are studying if this is not existing? We are studying because from this we will get some result, and with the help of those results, some other studies will become easy. Okay. So if the
Yes, sir.
transformer is 100% efficient, then the input power is equal to the output power. Input power is equal to the output power. Means the power you are giving at input, same amount of power you are getting at the output. Electrical power I am talking about.
Yes, sir.
The power input is equal to the power output.
Yes, sir.
Now power is potential difference into current. So at input there is primary winding. So we will write potential difference of primary, current of primary is equal to potential difference of secondary, current of secondary. At output you have secondary coil now. So you can write
Yes.
from here ES by EP is equal to IP by IS, and this is the another relation, and this relation is only valid for the transformer to be ideal or 100%.
Yes, sir. Yes.
Otherwise this expression will not be valid. Okay, so two expression is there. Okay, now generally what I am saying generally means in real life we have the practical transformer. Have you seen the transformer?
Yes, I have seen.
Okay, so obviously this transformer will not be 100% efficient, so the input power is not equal to the output power. Okay, so in this case the input power will always be greater than the output power. Why? Because there will be some losses also. For example, you can take the example of the laptop. Electrical energy you are providing to this laptop, not all
Yes,
the
sir.
electrical energy is converting into the work, or
Yes,
the
sir.
some energy is converted into the form of the heat. Okay, we are the heating of the laptop and all that. So
Yes, sir.
because some power or some energy is lost there also. Okay, so in this case it will become input power means ES must be greater than EPIP. So this is the expression. There is a term for the practical transformer, efficiency. Efficiency is represented by eta, and this efficiency is basically the output power divided by the input power
Input power.
multiplied by 100. So what will be the output power? Can you tell me? How can I write the output power for the transformer?
Output power of the transformer.
ES into IS. What will be the input power here?
EP.
Into IP
EP into IP. IPS.
multiplied by 100.
100.
So basically this will be the efficiency. Okay, so I think now you should write down this, and uh, this is finished.
Yes,
Transformer
sir.
is finished. Basically the working part is finished. Basically after that there will be a numerical and energy losses in the transformer, and this chapter will be finished from my side. And okay, so if we will have the class tomorrow, then we will finish it finally.
Yes, sir.
Okay, so got it now, means how the things are
Yes, sir.
going
Yes, yes, sir.
here.
Yes. Second column.
Yeah.
Can you scroll down?
Yeah. So this is the relation.
Yes, sir.
Basically, this is I suffix p. I suffix
Yes.
p. This is like this. Okay. So this is I, and this is p here. Like.
Second column.
Yeah. After this, we will solve one very simple question in 2 minutes. Then we will wind it up. Okay. In 2 minutes,
Yes,
I
sir.
can finish this question.
Yes, sir.
Hmm.
Done, sir.
Done. But before that, these two relation you have to remember. Okay, you have to write
Yes.
this. You have written now.
Yes.
So in the next class, we will discuss the energy losses in transformer.
Okay.
Okay. So there is one question. So before that, you should know the relation between ES by EP is equal to NS by NP.
And that's fine.
Also a relation ES by EP is equal to
IP bias.
IS, and this is valid always until and unless there is flux leakage is given, and this is valid
Yes.
for ideal condition.
Yes, sir.
So remember. So next question is based on this. This is the question. Okay, so in this question, ideal transformer is given primary coil and secondary coil is this.
Yes.
Okay, so number of turns in the primary coil 100, number of turns
Yes.
in the secondary coil is this,
200.
and input is given. What is the meaning of the input?
Input
What is
voltage.
the input
Like
voltage means? It is given that they have given. Just a minute. So I have to change my pen. It is given is ES is given
yes.
220 volt,
Yes, sir.
and IS is also given 10 ampere.
10 ampere.
This is given from the primary side, and NP is given 100. Okay, number of turns in the primary is 100 now,
Yes, sir.
and here this side
NS is
secondary
equal
side,
to 200.
yeah, NS is given 100 200, and we have to find IS and ES. This we have
Yes,
to
sir.
find. So first relation we know ES by EP
Yes,
is
is
equal
equal
to
to IP
tell me.
bias.
IP by IS, that is for ideal
Oh, yes.
transformer. valid,
NP by
valid.
NS.
That also will be valid because this is the ideal transformer.
Yes,
Okay,
sir.
this is the ideal transformer. So we can write NS by NP or IP by IS. So
Yeah.
if you are saying that,
Yes.
then I can write this IP by IS also. Okay, so I can write this also. Okay, no problem.
Yes, sir.
But we want to calculate something else. So first we will calculate that. So ES by EP is equal to NS by NP. I can write.
Yes, sir.
So now put the values. What is ES? We have to find. What is
ES is
EP?
220.
What is EP?
EP.
Hmm.
EP. EP is
220 volt.
220. Yes.
This is EP, na?
Yeah,
Primary
yeah,
voltage.
primary. Yeah. Sorry.
Sorry, I have written here ES. Sorry.
Yeah, that's.
Yeah. Okay, no problem. So is it? It is 220. What is
Yes.
NS? 200.
NS 200. Sir, NS is 200. Yes.
And this is 100.
Yeah.
So what you will get when you will cancel it out? You will get 2. So ES
Yes.
you will get 440 volt.
ES is 440 volts.
So can you tell me which type of transformer is this? Step down or step up?
So step up.
Yeah, step up. Also, you can see from the voltage also. Input voltage is less, output voltage is more.
More.
So we have calculated this ES.
Yes.
ES we have calculated. Now IS we want to calculate. So there is another relation.
Yeah. ES by
That
EP is equal
relation
to IS by IP. IP
ES by
IS.
EP. ES by EP is equal to
IP by IS.
IP by IS. So ES now we know
Yes,
440.
440.
This is
440 divided by
220.
220.
IP is 10.
10.
IS we have to calculate.
No, sir.
Now,
Sir, you wrote IS there. That's, you wrote IS is equal to 10 ampere in the given.
Oh, okay. It will be IP.
Yeah, it
Okay.
is IP.
No problem. So IS we can find it will become 2 5s are 10. So IS you will get 10 ampere, 5 ampere basically. So now you can see the value of the current. Current is less now.
Yes, sir.
So in step up, current becomes less, but
Yes, sir,
the
it is step up.
voltage becomes step up. So at the cost of the current, the voltage increases.
Because it increases.
Yeah. Okay, so now you can note down it. And so one last topic that is very 5-minute topic is left. That is energy lost in the transformer. Okay. And after that, electromagnetic wave will be there, and after that, optics will be there. Have you which chapters are going on in your school, Harsh?
Optics.
Wave or ray optics?
Ray optics. Ray optics.
Okay, ray optics. So how is that chapter?
It is confusing.
Confusing. NCERT has given the chapter electromagnetic wave before the optics. Why? The reason is that light is an electromagnetic wave.
Yes, sir.
So basically, reflection and refraction, interference, diffraction, and polarization. All these phenomena are happening. Why? Because of the light. These are the okay. Interference, reflection, and all these things are happening. This is the properties of light, na? Means
yes, sir.
Light is going through the reflection, light is going through the diffraction. So
yes,
NCERT had put that chapter before electromagnetic wave. Why? Because first you should know what is electromagnetic wave. Then you will know what will happen to the electromagnetic wave. First you should know what is electromagnetic wave. So that is why we study the electromagnetic wave, and after that there will be the chapter optics. So basically, electromagnetic wave, light is an electromagnetic wave.
Yes.
So first know about the light, then discuss the phenomena of the light.
Yes, sir.
So electromagnetic wave is basically a two lecture topic, or you can say two lecture unit. We will finish most probably in two lectures or maybe in three lectures, and after that ray optics will be started, and I think there will be the reduced syllabus this time from the ray optics.
Oh, so can you scroll down?
Yeah.
Done, sir.
Okay.